Today, the topic of our talk is to tell you about the results that were obtained using the telescope that you see in the picture here. It's called the Dark Energy Spectroscopic Instrument, or DESI in short. Has any of you heard about DESI here? Maybe we can do a show of hands before. Yeah, there's one at least. Okay, good. So, well, DESI has been in the news lately because of its recent results that came over a year ago and also a few months ago. And as the title says, these results hint at an evolving nature of the so-called dark energy, which we think is the reason for the accelerated expansion of our universe. So let's start with a brief history of the universe. It's shown as a schematic here. So the universe started with a big bang, after which it went on to expand, while also because of expansion started cooling down. And after about 400,000 years, it cooled enough so that the electrons and protons could combine and form the first atoms. And this era is called the recombination era or recombination epoch. And after recombination, when the first atoms formed, the radiation was no longer coupled or no longer interacting with these free electrons or protons, but instead it was free streaming. And so this is the radiation that traveled to us from the recombination era, which we call as the cosmic microwave background, or CMB. After recombination, there was a period of, again, dark ages during which these atoms and other ordinary matter, which we will call as baryons in the rest of the talk, started to grow and form structures under gravitational collapse. And eventually they formed the first stars and first galaxies, which emitted a UV radiation that then also heated the universe for a while. And in the last 13 or 12 billion years or so, the universe has, as it is right now in its fully evolved form, the adult universe that we see now has lots and lots of galaxies and clusters of galaxies and so on. And the interesting part is that we observe that these galaxies that are close to us, or in the late universe, as we call it, are receding from each other, drifting away from each other at an accelerating rate. Normally, if you put some galaxies together, you would think, okay, under gravity, they should come together, but they're instead actually moving away from each other at also an accelerated rate. And the rate of expansion of the universe as a whole is quantified by the Hubble parameter. And the key part of this talk is to understand how we actually measure this expansion rate and what it means for the cosmological model of the universe. So before we go to the measurements, we can briefly look at what the theory suggests. So from general relativity, and when you assume a homogeneous and isotropic universe, one can derive what's called the Friedmann equation for the universe that tells us what the expansion rate, or the Hubble parameter, should evolve like. So the rate of expansion depends on the total energy content of the universe. And the total energy content comprises the radiation, the matter component, which is both luminous and non-luminous matter, and this mysterious omega lambda that we see here that we call the dark energy. So in this expression, Z is the redshift. So you might have heard of Doppler redshifts before. Basically, if you have a source that's emitting light and it's moving away from you or towards you, you would see that the wavelength of the light is stretched or compressed depending on how the source is moving with respect to you. So it's the same phenomenon here. So this redshift is also the redshift, but in this case, it's the cosmological redshift that's occurring not because the source is moving relative to you, but because the source is in the universe, which itself is expanding. The space itself is stretching, so you see the wavelength of the light getting stretched. And this redshift, therefore, can tell us how far away an object that has emitted this light is from us. And in a way, it is also a proxy for the time, because the farther the object is, the earlier it would have had to emit the light that reached us. So although the relation between redshift and time is not exactly linear, in this talk we will consider high redshift as close to Big Bang or earlier times, and low redshift, we mean by low redshift we would mean local universe or later times in the variation of the universe. And in this expression, you also see these omega i's. So these are the normalized densities. Basically, they tell us how much of each of these components are there in the universe. So the plot here shows what the different energy densities of each of the components look like as a function of the redshift. Basically, I'm plotting each of these here. And so here, low redshift would be today, high redshift would be Big Bang, and redshift of 1000 would be recombination. And we see that in the beginning, the red curve is the one that dominates over the rest of the two. So radiation dominates matter. Eventually, there's an equality between radiation and matter. And later, there's an equality between radiation and dark energy, beyond which dark energy is the dominant component that is driving the Hubble parameter or the expansion of the universe. However, it was actually not always obvious to us that there should be a dark energy component, and that it's the reason for and it's also contributing to the expansion of the universe. So until the late 1990s, this was not really well understood. So in 1998, two different groups, using a technique that I'll shortly discuss, have discovered that the universe is not only expanding, but doing so at an accelerating rate. And if you look here, the deceleration parameter Q has this kind of form, which means that if deceleration has to be negative or acceleration to be positive, you need to have 1 plus 3 times omega less than 0, or W greater than minus 1/3. And simply rearranging the terms in this kind of parameterization from the previous slide, we see that radiation and matter have positive W, but dark energy has this W minus 1. So if you see an acceleration in the expansion of the universe, only a component like dark energy can be responsible for it. And this model, together with the matter, radiation, and dark energy, is thought of as the standard model of cosmology, or the lambda CDM model. Right. So how do we know that the universe has been expanding at an accelerated rate? So there are a couple of ways to measure the expansion history of the universe. One is using what are called standard candles. Laura will discuss about the second method that's based on using standard rulers. So the basic idea of standard candles is simple. So if you know a source whose intrinsic luminosity that you can predict very precisely, then if you can measure its apparent brightness as well, then taking the ratio of the apparent brightness to the intrinsic luminosity should tell you how far this source is, because the apparent brightness goes as intrinsic brightness over R squared roughly. So supernovae, or if you haven't heard supernovae are just these stars that are dying in a very dramatic fashion. So supernovae form a standard candle. We very well know how to predict their intrinsic brightness. And the teams that I was mentioning about, they also won a Nobel Prize for measuring this. What they did was they took these supernovae and measured their luminosity distances that are plotted on the y-axis here. On the other hand, you can also measure the velocities of these sources, supernovae, from the redshifts. So you can take the spectrum of supernovae that gives you the emission lines, and depending on how the emission lines shifted, you can measure its redshift. And this redshift is a proxy for the velocity. And this distance versus redshift curve is what's called the Hubble diagram. And one can then repeat this observation for several objects, and then fit a curve to this Hubble diagram according to this Hubble's law. And the slope of this curve is what gives us the Hubble parameter h, or the expansion rate. And so what this team showed is that the supernovae observations could not be fit by a non-accelerating universe. I think it's not very clear here, with 100% matter and omega lambda taken to be zero. And their data showed that you need to have a dark energy component that is almost 65% of the total matter content of the universe. Yeah, and Laura will now explain about Standard Ruler.
Yeah, so our goal here is to look at the expansion history of the universe to understand what dark energy is. So as Sindhu said, we have the standard candles, which we know the distance they are from us because we know how bright they are. So depending on how bright or faint we see them, we know how far away they are. But we have another method, which is the one we actually have used for the results that we'll be explaining at the end of the talk, which is called standard ruler. And the idea of a standard ruler is that if you know a certain length, at like you know what this ruler is in length at some point in time in the universe, then looking at how big or small it is at different times, so as the universe expands, it gets bigger. By looking at its length, you can infer how big the universe is at that time. So the standard ruler we use for in DESI is called the Baryon Acoustic Oscillations, or BAO. So what is a BAO? I don't know if anybody here knows. No? Okay, well. So the idea is that in the early universe, we have a plasma where the photons, which is the radiation Cindy was talking about, and the baryons, so electrons, protons, and neutrons, are all coupled. This means that they all interact together, like kind of in a soup, and they all move together. And this plasma is not completely homogeneous. There are certain parts that have more density than others. So here I've tried to paint this as points. Obviously, it's not like this. This is like a cartoon depiction of it. But that's the idea. We have a plasma of photons and baryons with some regions that are more dense than others. So let's look at what happened in one of those overdense regions, so one of these points. So here you can see a GIF. This like peak would be one of the points that is overdense. And actually in the early universe, due to pressure from the photons, there was a sound wave created from these density peaks that pulls the photons along with the baryons out in this kind of ring form. So we end up with an overdensity in the middle and an overdensity that looks like a ring at a certain distance from this peak. And this wave stopped propagating at the time of recombination. So when the universe expanded more, it became more cold, and the photons and the baryons stopped being coupled. The baryons started creating hydrogen atoms, and we didn't have any plasma anymore, and the wave stopped. And it stopped at a certain distance from the peak in the middle. So this distance from the peak to the ring is our standard ruler, what we are trying to measure. We know how big this is. Yeah, how can we use this length to infer anything about the expansion of the universe? So yeah, as I said before, we know the length of this ruler in co-moving coordinates, or today it's of 150 megaparsecs. A megaparsec is just like a distance unit, that's 3.26 million light years. And we usually refer to this length as the sound horizon, or RD, just because we'll see it later in some formulas. So yeah, the idea is that in time, this ring becomes bigger because the universe expands. So we can measure this length. at different times, and then know how big the universe is at these different times. And from there, know at what rate it is expanding. So in reality, it's more complicated because we have a lot of rings. Yeah. But that's the main idea. So how can we see these rings? Well, these rings of overdensity and the peak in the middle is where galaxies are more likely to be created. So when we look at the galaxies nowadays, we see that if we have a galaxy here, we're more likely to have one at a distance of the BAO distance than to have a galaxy like, for example, here. It's a probability thing and it's not that easy, but yeah, we are more likely to find galaxies separated by a distance of this ruler. So with that in mind, there you go.
There.
Okay. Yeah. Yeah, so we can look at video in two ways. So imagine like a telescope on Earth, which is DESI, which I'll talk about in a minute. You can look at the galaxies, see the distance between them, and find out at what distance you're more likely to find them, and infer what the BAO peak is, which I'll explain now. But you can do this in two ways. You can look at this distance transversely to your telescope. So you would get like an angle at which you are more likely to find galaxies. This angle is equal to RD divided by the distance from the telescope to the redshift. Or you can also look at this distance in the line of sight in this way. And this is actually good having two ways because we can break some degeneracies that we would have if not. I'll explain that later, but this is the idea. We measure it in two different ways. And when we look at the separation of galaxies, you can plot, for example, the how probable it is to find the galaxies at different distances. So here you see distances from 60 to 140 megaparsecs over h, where h is just 0.7. And we find a function that looks like this with a peak here in the middle with an extra correlation that you wouldn't expect otherwise. And this peak is what corresponds to the BAO distance. So the telescope we use to look at all these galaxies is DESI, the Dark Energy Spectroscopic Instrument that Cindy mentioned before. It's in Arizona. It's 4 meters tall, and it's what we call a large like scale survey. It maps a big part of the sky. You can see it in this plot here. And this survey or this telescope will be looking at galaxies for 5 years, and it will detect in total 40 million galaxies. So the results from 1 year of observations came out 1 year ago. That's what we call DR1. And the results from 3 years of observation came out in March of this year. That's what we call DR2. And both the DR1 and DR2 results gave very unexpected results, which we will talk about in the end. And yeah. So DESI, as I said before, you need to measure the BAO at different times to know how the universe has been expanding. Different times would be different redshifts for us. So the higher the redshift, the longer ago, so the earlier the time. And it looks at a lot of different tracers or types of galaxies. And these ones here, you can see the BAO peak for all of them. And Sindhu and I work on Lima Alpha Forest, which is the tracer that uses that's at highest redshift, so furthest away from us and at earlier times. And Sindhu will explain a bit about what this tracer is.
Yeah, I hope you're all still with us here. Okay, right. As Laura just explained, we have these tracers of matter and we want to measure how clustered matter is that gives us the BAO length scale, and you want to measure that at different times. And as she just showed us a plot of the correlation function that was measured from different galaxies, how based on how galaxies cluster. But galaxies are only so bright. They're not bright enough that they can be observed out to very far distances. You need an even brighter source to be able to detect the matter distribution at higher redshifts or longer back in time. And so DESI also looks at these objects called quasars. Quasars are basically accreting supermassive black holes. So almost all massive galaxies have a supermassive black hole at their center. Our own galaxy has a million solar mass black hole at its center. And so when these supermassive black holes are accreting matter, they emit like copious amounts of radiation, which are visible to us as a quasar. And these quasars are really luminous. One of them can outshine an entire galaxy consisting of like a trillion stars. So given that they're so bright, we can observe them out to very large redshifts. But because they're this far, two things happen to the quasar light while it travels from the quasar to us. First is that it has to travel through the universe. And so because of the expansion of the space itself, the wavelength of this light is getting stretched. So the bottom panel here is showing the spectrum of a quasar, which is basically observed wavelength and the intensity on the y-axis. And the dashed red curve is what the emission from this quasar would look like if you were very close to the quasar. And for example, you see that it's a nice power law with a lot of emission lines coming from different atoms that are close to the quasar. So for example, you might have heard of the hydrogen emission lines, the Lyman series, Palmer-Paschen series. And so this emission line that you see here, the strongest one comes from the emission from hydrogen that corresponds to the n equals 2 to 1 or the Lyman alpha transition line. And this at rest frame should be at 1216 angstroms, but when we observe it, it is at a much higher wavelength simply because it had to undergo redshifting because of the expansion of space. Second thing, when the quasar light travels to us, it is also encountering a lot of the intervening gas that's between the quasar and us. And so there are these clouds of neutral hydrogen gas that are in the intergalactic medium, which is the space between the galaxies, that can absorb and scatter away the photons from the quasar and create these dark absorption lines or dark lines that you see in the quasar spectrum. These series of absorption lines are what we call the Lyman alpha forest, mainly because the absorption is happening between the n equals 1 to 2 transition of the hydrogen. And so each time there is an absorption line in the quasar spectrum, you know that there is a corresponding neutral hydrogen gas cloud that has absorbed it. And so by looking at the distribution of all these clouds, you can trace what the matter distribution or the matter clustering should have been like. And basically, as Laura said, if you have two quasars and two spectra taken, you know where the neutral hydrogen gas clouds are, and then you can measure the correlation function, which gives us the probability of finding two neutral hydrogen gas clouds within a given separation R. So to give an analogy, you can think of each of you in this room or each seat in this room as a pixel of the quasar spectra. And for example, since a lot of you are wearing white t-shirts, we can think of each person wearing a white t-shirt as a neutral hydrogen gas cloud. Now, if the neutral hydrogen was all randomly distributed, like I think most of you are also randomly seated here, the correlation would be very weak and you wouldn't see any signal. But if there was a preference for a particular type of, if there was a preference for the people with white shirts sitting in this room, maybe because of the Wi-Fi or cooling or whatever, then depending on how many seats you have between each of these white shirt wearing people, you can measure where the peak in the correlation function should be. And so this is what the correlation function is measuring. And As you see, there is a certain peak that corresponds to the BAO scale that tells us at what scale the matter is more clustered than randomly. And this peak of BAO is can be derived from theory and is dependent on the cosmological parameters that we've been talking about, the omegas and the H naught and so on. And Laura will now explain how this peak can be used to constrain the different matter components in the expansion history of the universe.
Yeah, so yeah, measuring this BAO peak gives us information about the universe. So Sindhu said before that the most standard model of the universe is the one we call lambda CDM. The omegas tell us the density today of the different components of matter or radiation or of dark energy. And H, which is the Hubble parameter, tells us the expansion of the universe, and it depends on redshift, so it changes over time. So if you remember, we could look at the BAO peak in the transverse direction. Yeah, and it was equal to RD, so the.
Perdón. Sorry. What is it?
I don't know.
I'll just go back and.
Sorry. Okay.
Sorry.
Okay.
That's it.
Is it good?
Yeah. Solo quería to get it.
Like, okay. Well,
Sorry.
is it okay? No.
Sí, sí, sí.
Oh my God. Okay, so you find this angle at which you see galaxies being separated more often, which is equal to RD. So the distance from the peak to the ring, and the M, so the distance from the telescope to Z. And you can expand this in terms of H, the Hubble expansion, and C is just the speed of light. And this Hubble expansion, you can put it as the expansion to date, which would be H naught or H0, times a function E of Z, which depends on redshift or on time. So if we assume lambda CDM, the standard model for the universe, we can write this E of Z as a function of our omegas. And omega lambda can actually be substituted by 1 minus omega matter. So in the end, we obtain this as a function of RD, H naught, and omega matter. And this is what we call a degeneracy. I don't know if you know what this is, but it means that for a value of theta that we find, we can't actually find out what the values of these parameters are, because you can, by modifying the three of them up and down, you can still get the same value of theta. So this creates a degeneracy between these three parameters. And this is where having the other BAO measurement, so the one from the line of sight, is useful, because the redshift interval in which you're more likely to find galaxies separated is also a function of RD, H naught, and E of Z, which depends on omega matter. So now you have two formulas for three variables, so you can break one of the degeneracies. And this is how, from the BAO peak, you can find information about the universe. So the results we will show now are all assuming the lambda CDM model that Sindhu explained before of the universe. And we will show them all using contour plots. So I'm not sure if you're familiar with what a contour plot is, but if you have two variables, x in the x-axis and y in the y-axis, it tells you which values are more probable for these two parameters. So the inner circle is what we call 1 sigma, which tells us the most probable values of these two parameters with a 68% confidence. And then we usually also plot the 2 sigma contour, which gives it with a 95% confidence. So all the results of all the parameters, we will show them in this way. And we can also use these sigmas to tell tensions between different contours. So imagine you have this contour here, and you have a contour that is similar, but in another place. They are in tension. They are not agreeing with the values of y and x. So if we say they are in a 2 sigma tension, this means that they agree by a factor that by chance would only happen like 5%, so they don't agree much. And normally when we say 1 sigma tension, it's not concerning. This is very normal. 2 sigma tension is worth noticing, but it's not too worrying. And 3 sigma or more is very important discrepancy. So this is just so you can understand the results we'll explain now. So we obtain a contour plots for omega matter, the density of matter today, and then H naught times RD for all of the different tracers from DESI. So the quasars, the different types of galaxies, in purple the Lyman alpha tracer, which Sig will explain. And then by combining them all, we get this constraint in the middle, the black one, which is the final result from DESI for the value of omega matter and H naught times RD. So once we have this, we can compare the values DESI obtained with the values other surveys have obtained for omega matter. So with DESI, we are looking at the video in this area of the timeline of the universe, so late times, close to us. But there are other surveys that look at VAO in much earlier times, in particular in the CMB. And the results they obtained for these values actually don't agree with what we obtained. So we obtained this blue contour. The black dashed one is the one we obtained from 1 year of observation, so our old result. And the one they obtained from the CMB is this pink contour here. So you can see that the CMB tells you that omega matter is higher values than the ones that DESI tells you. Yeah, and the discrepancy right now with the 3 years of observations is of 2.3 sigma, which is worth noticing and worth exploring. But as I said before, these are constraints assuming the lambda CDM model of the universe, and maybe there's a different model of the universe that could explain this, and that way we would have an agreement between the results of different surveys. And that's what Cindy is going to explain now.
Okay. Right. So as Lara just told us, there's a discrepancy in the measurements of this omega matter between different surveys. And so what the DESI collaboration did was to look at a different model than the lambda CDM model, which is the dynamical dark energy model here. So if you recall the Friedman equation again, instead of assuming the omega lambda to be a constant, we now assume a model, take a model where it evolves with redshift with this particular parameterization for the power W of A, which goes as follows. A is just 1/1 plus Z. And so with such a parameterization, you can again look at the correlation functions, fit them to this new cosmological model, and extract the same cosmological parameters. And here on the right side, I'm showing the contours again for the best fit values of W0 and WA. And a WA of 0 and W0 of -1 will correspond to the lambda CDM model. And we see that the best fit parameters from this dynamical dark energy model prefer from the DESI data, both first and second data releases prefer a much larger value for W0 and lower value for WA. So, but still, the lambda CDM values of W0, WA are within the 2 sigma contours of these of the best fit parameters. So it's it doesn't appear to be as in a great disagreement with the lambda CDM model. However, when we combine the inference of these parameters using information from the CMB surveys, we see a stronger preference for the W0 WA model. So again, the big contours here show the best fit for W0 and WA when you use both DESI data as well as CMB data. And so this shows a stronger preference for that evolving dark energy compared to the lambda CDM model. Finally, we can also combine the information that we have about these parameters from the supernovae or standard candles that I mentioned in the beginning of the talk. And for three different data sets of these supernovae, we still see that the preferred values of W0 or WA are much, much farther from the lambda CDM values for these parameters. So in fact, they can be as large as 4 sigma in 4 sigma disagreement with the lambda CDM model, which, as Laura told us, anything greater than 3 sigma is worth worrying about. So, to summarize, like DESI results do suggest that there could be an evolving component of dark energy in the universe, which is exciting because the lambda CDM or standard model of cosmology, the standard model of cosmology was assumed to be the lambda CDM model for over three decades now, and so this is something exciting if dark energy is indeed evolving.
Yes. Yeah, so just as a summary of everything we have said, which I think is a lot, the universe is made of matter, radiation, and dark energy, and it's expanding, and it's expanding at an accelerated rate, and this is due to dark energy, but we don't know what dark energy is. We just know it's there because we know the universe is expanding faster and faster. So we hope that by studying this expansion, we can understand something about dark energy, and that's what DESI tries to do. Using BAO, which is a standard ruler, which can tell you the size of the universe at different times, and then you can obtain this expansion rate. And the latest results show tensions with the most standard model of the universe that has been assumed for the past few decades. And one possible explanation DESI gives is that dark energy might not be a constant in the formulas that Sindhu showed. This is, of course, not, it doesn't have to be the explanation. There could be problems with the systematics, or there could be other things that people are investigating too. But this would be a really cool explanation and would give us a shift in how we understand the universe. So yeah, that's all. Thanks.